We're going to start talking about feedback. And the first thing that we're going to do is list when it is used and what it's used for. So these are the things that feedback can help with. So the first thing that makes feedback useful is that it can give us more control over the game or make the design less sensitive to the game. So we call that desensitize the game. We can also reduce nonlinear distortion, and all these use cases are related, but by making your design less sensitive to the game, you can also reduce the nonlinear distortion because your design will tend to saturate or will tend to not saturate if you have a good control of the game. So that's another usefulness of feedback. We can also reduce the effect of noise, again by controlling the game more effectively. We can control more effectively input and output impedance. So that's control input and another thing that is very useful, that feedback is very useful for, is to extend the bandwidth of a circuit or a system. And we will talk about the gain bandwidth product exhibited by components like op amps, and we will see that when we apply feedback to the circuits and we change the gain, we can also extend the bandwidth by making the gain smaller and having more control over it. We can extend the bandwidth of operation of the circuit. So a lot of useful features for feedback. So it really deserves that we spend some time treating that that subject matter in detail. So let's look at how feedback reduces the gain by the amount of feedback. So let's see how feedback reduces the gain by what we're going to introduce as the amount of feedback. And to do that, we're going to start by representing some system that had some forward open loop gain denoted as A. And over here, we're going to have an input to that system. And the system has an output. Now we're going to sample the output and process that through a feedback network going back towards the input, and we're going to couple that processed sampling of the output with the input, and that's going to be our feedback signal. And then what we apply to our system is this signal here, which is really an error signal. So if we look at this diagram, we can write these very simple expressions. So the output is going to be equal to the gain A, or open loop gain, times the error. The feedback signal is going to be the gain of the feedback network times the output, and the error signal is the difference between the input and the feedback signal. Now, given those relationships, now let's define the closed loop gain of the system. So the closed loop gain of the system, denoted as A sub f, or the gain with feedback, is the actual output over the input. And if we look at the previous relationships that we had stipulated, that can be written as A divided by 1 plus A beta. And here, the quantity A beta is defined as the loop gain. Different from A, which is the open loop gain, or just the gain of the system without any feedback. But when you apply the feedback, A times beta become the loop gain. And the quantity that divides that open loop gain in the closed loop gain expression is the amount of feedback that we defined. So 1 plus A beta is defined as the amount of feedback. Now, if the loop gain is much greater than 1, which is the case, because normally the open loop gain is very, very high, then you can see from the expression of the closed loop gain that AF, or the closed loop gain, can be approximated by 1 over beta, which is defined as the ideal or the best case that you can have for the closed loop gain. So you can see that if this term over here is much greater than 1, then I can ignore the 1, the a's cancel, and this is 1 over beta if A beta is much greater than 1. Now, another way of looking at this, at the closed loop gain, is that the closed loop gain can be written as the following. if I introduce this term here, then I can write the closed loop gain as follows. Then since 1 over beta is the ideal closed loop gain, this term becomes, as we defined it, we define that so this expression that multiplies the ideal closed loop gain to give us the actual closed loop gain here is the amount. We can look at that as the amount. The amount that the closed loop gain, the actual loop gain, deviates from the ideal due to the feedback. Okay, so, and you can see that normally we get very close. We get very close to the ideal because this term, that amount that AF deviates from the ideal open loop closed loop gain is very close to 1. So if normally A beta is very high, then essentially this term will be close to 0, and then this term would be close to 1. So what we do next time is start with an example of how, so we can see numerically how that happens and how that amounts that the closed loop gain deviates from the ideal works out due to some actual numerical values. And we'll stop here for today. Thanks.